Good day, CET 103 students. I'm coming to you from a Zoom feed. I apologize. I tried to put up the second video in the series of horizontal curves last evening, and I must have made the file too large, so it wasn't able to get it and have glitches posting that. So this today is one to follow up with that. I'm sure that many of you probably got into the assignment part of that and you said, wow, how do I do this? And I would hope that I would have expected that you probably would have had that problem. So today I'm going to try to be using a couple of things. We use the homework assignment, and then I'm going to use something that's a little bit different for me today, which is I'm going to use sketching on the tool that I have for Zoom here. It's a little cumbersome, in which I'm going to be able to write with my finger on the screen. So it may be a little bit difficult, but I think we can get it done. So apologize for some of the maybe graphics in a little bit in advance, because it is a little bit difficult. Start out here with the screen share, and I'm going to share the slides with you all first. Okay, going into the slide information. This is the slides that I sent you out originally, and this was in the, and here is the homework assignment. A little bit about what we have. This is a typical roadway scenario situation that we may encounter within a field. Let me sort of tell you what we have here is we have a tangent line coming in, and we have a tangent line going out. The intention of the design engineer here is to put in a curved piece of roadway here that would transition from one curve going in one tangent going in, one tangent going out. In order to solve any horizontal curve, we need at least two pieces of information about that curve that comes from some of the elements that are in the field. In this situation, we have been given two very important pieces of information, one being the delta or central angle, or this angle right here that you see, deflection angle. There's different words. I've talked about that in our last video series. Also, we see that we've been given the radius point. The radius point is the point from here to here. That's a distance of what we will call radius R. And that is an important computation piece within the calculations of this. Also, this handout I've given you has the formulas that are probably required to do each of these computations over here on the side. So this is almost sort of a plug and play sort of assignment, but I'm going to walk through it with you today. Over here off to the right-hand side are some commonly used equations that we use you will find in the industry. Your textbook probably lists a lot of your horizontal curve formulas, but then in addition to that, I've put these on there for you to use in the future should you ever need to. This is particularly important for those of you who may be CET majors and may have aspirations for taking the fundamentals of engineering exam later on in your careers, because this is going to be, these formulas will be required at that time. Also, as you head on into your highway design class, these are very important. But before we get started, I'm going to explain what we have here. Okay, here we have our horizontal curve coming in, our horizontal curve, our horizontal tangent coming in, or our straight line coming in, our straight line deflecting out. The design engineer has decided to come back a certain distance right here, begin right here, and then curve and transition into here. You will notice right here that we have the station of the PI, which is the point of intersection. The point of intersection means where the two lines intersect. Since we have the station of that, we can then use that information to calculate the stations of the other necessary components within the curve. We notice we have a T, which is the tangent distance here. We don't have the tangent distance, so we're going to have to compute it over here. Also over here, we have the PC station, which is not given. We're going to have to compute that given our data. We have the tangent length going out. Remember, in a simple horizontal curve, this length and this length must be the same. That's what's called an equal tangent curve. And that's what we're to be working with, or a simple curve. It also is asking over here for the PT station. So given our information here and this information, what we're going to do is we're going to calculate the station of the PC, calculate the station of the PT. We're also going to calculate, as we get into part F through J here in our handout, is we're going to calculate some of the method, some of the tools that we would use to lay out points along this curve so that we could give the builder this information in the field. I'm going to show you how to do those computations here as we progress through the video. So please bear with me, and hopefully this isn't going to be too painful. So that being said, I'm going to come down here and stop this share, and I'm going to share the other screen with you, which is the whiteboard. Okay, I am going to now go to full screen with the whiteboard, and I'm going to start out by, let's see if I bar up here to the side, and I'm going to start out by drawing some lines here. I'm going to start out by trying to replicate what you had on the other slides right there, where this right here is going to be our deflection angle. Also, we know that this particular point right here is the PI, and the PI station was 16 plus 94.50. So I am going to use that information to begin to do our calculations. If you notice the first equation there, it says A is to find the delta angle and divide it by 2, or the deflection angle. So if you notice right there, the deflection angle was given to us, and that's this angle right here. And it was given to us as to be 21 degrees, and this angle right here was 43 degrees, 24 minutes, 20 seconds. So in that situation, you have to take that angular measurement, divide by 2. If you remember when we were doing our angular measurements earlier on in the semester, we'll have to take that because that information is given to us in degrees, minutes, and seconds. I will then take that and convert that to decimal degrees and divide it by 2. If I divide it by 2, my delta over 2, would be equal to 21 degrees, 48 minutes, and 10 seconds. That is simply taking the angular measurement given there, which is the 43 degrees, 24 minutes, 20 seconds, and dividing that into 2. So that would be the answer to part A right there of that sheet. Now I'm going to go ahead and progress on to the other pieces of information. Let me erase out here so we can get us some space here, and I'm going to go back into my drawing tools. Okay, at this stage in the game, what I'd like to do now is come in and talk and calculate the tangent. Now, if you notice, the tangent is this distance that comes back here and shows where the curve begins. This is our tangent length right here. Our tangent length is defined, apologize, my finger must be a little big there. So let me try to do that, my equal sign just a little bit better there. Okay, so here's the tangent length. The tangent length, if you look at the formula, is equal to the radius divided by, or I'm sorry, the radius multiplied by the tangent function of the delta over 2, which is the number we just calculated. So therefore, you would have to take the tangent function of 21 degrees, 42 minutes, and 10 seconds. Again, remember that you would have to convert that to decimal degrees and then compute that in your calculator. You would take the tangent function and then multiply it by the radius, which you've been given right there, and that is 550 feet. So therefore, our tangent length would equal 218 That is what I get when I compute. So that 218 feet is the distance here and the distance here as we go along to our curve. So basically what we've done is we've defined that. Remember, this t and this t are equal. My sketch may not show that, but that's the intention. Okay, so the next part of it is to calculate the length. Well, what is the length? Well, the length would be the curve, the length along the curvature, which is right here. So that is our L. L is right there, and that is the length of the curve. So as you can see now, we're developing similar to what we saw on the sketch yesterday, which talked about the components of the curve. The length of the curve is defined as taking the delta or the deflection angle, intersection angle, whichever one you like to call, is this angle right up here, and taking that angle and converting that angle into the length, and you take that, the formula says to take this angle right here, and which is in our situation 43 degrees, 24 minutes, 20 seconds. We divide that by 360 degrees, and then you multiply that times pi times d. The d in this situation is the diameter, or twice the radius. So that is key in this thing, and unfortunately that equation doesn't really tell us that. But in equation on problem C, the d stands for diameter, which is 2 times the radius. You may want to make that note on your handout so that you see that in the future. So if you were to take the deflection angle divided by 360, multiply times pi times the diameter, the tangent length, not the tangent length, but the length of the curve here is going to be L, I'll put it over here, is equal to 416.66. Now, here's one of those points where I kind of look at my curve data and I say, does that make sense to me? As I told you, in the surveying business, it's always sort of the difficult part is, are our computations right? Well, if you look at our tangent length, which is 218 feet going back toward the beginning of the project, and 218 feet going ahead on the next tangent, you'll notice that those two distances are 218 and 218 because it's an equal tangent curve. So if you were to just compute those and add those together, that gives you something in the neighborhoods of about 436 feet roughly. And if you notice over here, our length of curve is smaller than that. That's usually a general indication for me that my number makes sense, because just graphically it's the curvature, or that particular distance, is going to be shorter than the distance of those two lines put together. That being said, I'm going to progress on to part B, which is the calculation of the PC station. I calculate the PC station by taking the PT station with, the PI station. I'm going to take the PI station, and this is stationed, and I am going to subtract the tangent length. Okay, so this is going to be equal to the PC. So therefore, the PC is going to be equal to 1,694.50, which is this right here. This is my PI station. And I am going to subtract my tangent length of 218.90. Therefore, my PC station is equal to 1475/60, or 14 plus 75/60. That is going to be the station at this point right here. That is the station for the PC of this calculation. Now I'm going to go ahead, and I'm at almost 14 minutes for my video. I'm going to try to keep this one under 15. So I am going to go ahead and go to my eraser right now. I will erase out this information just because I'd like to use this space to calculate the next piece of it. The next piece of this is going to be the calculation of the PT station. So the PC station we do now know, and the PC station we do now know. Let's see, let me go to my drawing tools. PC is right here. Now, in order to calculate the PT station, which would be this point right here, the PT is equal to the PC plus the length of the curve. Be very careful about this. One of the common mistakes in calculating horizontal curves is that someone will take the PI station and add this tangent length to it to come up with the station of the PT. That is not correct. The proper procedure is to follow along from the beginning of the project. So you'll find the station of the point of curvature, or PC, and add the length of the curve to get to the PT station. So if you take the PT, to calculate the PT station, you take the PC plus the length. In this situation, that's going to be the PC station is 1475/60, or 1475.60, plus the length of the curve. We calculated the length of the curve to be 416.66. So therefore, our PT station will be equal to 18 plus 92.26. 18 plus 92.26. And that is the station of the PT. I am going to stop this video here for us now and progress on as we come back in the next series, and I'll talk to you about items F through J on the slides. Thank you, and I am going to stop our share now and stop this recording.